Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 31st, 2025, about 4 days ago. This paper introduces next vector prediction, compressing k tokens into one continuous vector that reconstructs with over 99.9% accuracy, cutting steps by a factor of k and, at k equals 4, matching a strong discrete baseline with 44% fewer training flops and 34% fewer inference flops. The paper is titled Continuous Autoregressive Language Models, and as we will see later, the implications for model efficiency and controllable sampling are quite significant. Also, the authors shared a GitHub repo. It's the official Calm implementation with code for the Autoencoder and continuous LM, training scripts for energy-based, diffusion, and flow variants, a baseline AR model, tokenizer assets, and data prep. You'll find requirements, step-by-step run scripts, and downloadable checkpoints with evaluation. On Hugging Face, Calm offers M, L, and XL weights, with model cards, dataset details, and links to training, evaluation, and sampling examples so you can run it quickly. Alright, Figure 1 shows the core idea that faster generation comes from predicting fewer, richer units. An autoencoder, which is a compact compressor and reconstructor, maps k tokens to one vector, so sequence length drops by about k. The left side depicts token-by-token prediction, which requires many steps. The right side replaces that with vector-by-vector prediction, so the model advances in larger semantic chunks and spends less compute per sentence. So Figure 2 shows the full architecture and why generation stays efficient. The pipeline compresses k tokens, feeds a transformer to produce a hidden state, then a small energy-based generative head refines random noise into one vector that the autoencoder decoder turns back into k tokens. Energy-based here means a scoring network that nudges samples toward plausible vectors. The left panel depicts the token-grounded input path, while the right panel expands one residual MLP block in the head. So Table 1 compares compute cost and quality between standard transformers and the continuous model at k equals 4. The takeaway is that predicting vectors lets similar quality arrive with fewer floating point operations. Breyer LM, a likelihood-free metric based on the Breyer score that tracks predictive accuracy, stays competitive across sizes. Calm M matches the small transformer while cutting training flops by 44%. It also trims inference flops by 34%, which means faster generation per token. Figure 4 shows how chunk size changes the efficiency sweet spot. Chunk size k means how many tokens get compressed into one vector per step, so a larger k increases semantic bandwidth. The curve with squares rises as k increases to 4, which lifts Breyer LM at lower training FLOPs than the transformer line. K equals 1 sits below the transformer because continuous prediction is harder, while k equals 8 drops, suggesting the model needs more capacity. Wrapping up, 2 takeaways stand out. Next vector prediction boosts semantic bandwidth, so generation needs far fewer steps, and with k near 4, it matches strong baselines while cutting compute. The supporting toolkit, energy-based head, Breyer LM, and temperature sampling points to cheaper, greener, more controllable language models. That is it for the AI Research Roundup. I am Alex, thanks for listening.